In this lesson, we're going to talk about what makes an element an isotope and why some are more common. So an isotope of an element has the same number of protons and electrons, but a different number of neutrons. So this means since we have a different number of neutrons, each isotope has a different mass number. Which is how we distinguish the isotopes apart from each other. So if we look at carbon as an example, we'll look at carbon 12, carbon 13, and carbon 14. In this notation, the value listed behind the element's name is just its mass number, which, like I said, is how we distinguish them. So carbon 12, we know, has 6 protons, and using this notation, we know its mass number is 12, so that means it has 6 neutrons. Carbon 13, again, 6 protons. We see it as 13 as its mass number, so it has 7 neutrons. Carbon 14, again, 6 protons, a mass number of 14, which means it has 8 neutrons. And so another notation that we can use when writing isotopes is like this, where we use the element symbol, and in the lower left-hand corner, we write its atomic number, which is 6 in this case, and in the upper left-hand corner, we write the mass number, which would be 12 for carbon 12. And then for carbon 13 and carbon 14, it follows that similar pattern. So that's just another notation that you can use when writing out isotopes. And the second part of the question is why some isotopes are more common. And this comes down to atomic stability, which deals with the atomic and electromagnetic forces. And it also deals with the excess number of neutrons. Because we said that each isotope has a different number of neutrons. So when something has these excess number of neutrons, it wants to get rid of them, and it does that through radioactive decay. So radioactive decay is when it is emitting these excess neutrons as well as protons from the nucleus until it reaches the stable form. And so, looking at this, we can tell that something that has more excess neutrons, it's going to be more unstable because it's further from its natural element state. And since it's more unstable, it's going to be more apt to undergo radioactive decay to reach a stable form. And so, like, if we go back up to our carbon example, we see that carbon 12 has no excess neutrons, so it's stable. And carbon 13 only has 1 excess neutron, so it doesn't have too many extra, so it's also going to be stable. So those really won't undergo radioactive decay. Carbon 14, on the other hand, has 2 excess neutrons. So we would classify this as unstable, and it will undergo radioactive decay to reach a stable form. And so, like I said, stable isotopes have not been seen to undergo radioactive decay. Because they're already happy in their current stable state. And so this is why some are more common, because the stable isotopes with few excess neutrons are happy as they are, and the unstable isotopes, which have more excess neutrons, will undergo radioactive decay until they reach a stable form.